So how do we know what we've actually grown? How do we know what comes out of the growth chamber? Well, one of the most important fundamental tools for knowing what kind of silicon germanium we've deposited is X-ray diffraction. X-rays have wavelengths similar to the spacing between the atoms in the crystal of silicon germanium. And in fact, because germanium is slightly bigger than silicon, germanium is 4.2% bigger than silicon in terms of the spacing between the atoms. And there's a relatively linear relationship, not exactly linear, but relatively linear relationship between the germanium content and the lattice parameter. This means that if we measure the spacing between the atoms in a silicon germanium crystal, we can figure out exactly how much germanium is inside the crystal to a very high degree of accuracy. And X-ray diffraction helps us do this. If we do it at high resolution, which is now industrially and technically very easy, everything's easy if you have enough resources. Technically very easy now, technically standard to make diffraction measurements at a high resolution that allow us to measure the amount of germanium in the silicon germanium. And this is the most fundamental thing to know, because if we want a silicon germanium virtual substrate that stops at 70%, we have to know how much gas to put in the chamber to give us 70% silicon germanium. At a slightly higher level, a diffraction experiment is a Fourier transform of the structure of the semiconductor. And at the most basic level, that means that if there's a periodic structure of atoms, there is a peak in the diffraction. But at a slightly more interesting level, that means that if we have a thin layer, for example, a germanium quantum well, then what we will see in the diffraction pattern is the Fourier transform of a rectangular structure. And of course, the Fourier transform of a rectangular structure is a sinc, a cardinal sign. So we see that function squared in the intensity. And what you can see here in the diffraction pattern on the left is indeed the germanium quantum well with some fringes on either side, which tell us the thickness of the quantum well. And as you can see on the reciprocal space map on the left, the germanium quantum well is vertically aligned below the virtual substrate. That means it has the same lattice parameter as the virtual substrate, so it's strained according to the graded buffer that we've grown it on. We can see a slight peak coming from the barrier layers and the cap that show us that the cap is maybe not exactly the same composition as the virtual substrate. This peak is also visible in the diffraction scan. Making a simulation of this with a dynamical simulation package allows us to fit a quantum well profile that matches this diffraction pattern. It's not a unique determination because there are many profiles which would give a similar diffraction pattern, but now we can be sure, or at least we can be sure that this candidate for our quantum well profile is fitting with the experimental data. And this shows us, for example, the true germanium content in the quantum well, and will also give us information about how sharp the interfaces are. Part of the information about the profile needs to come from other characterization techniques. A fairly direct way of observing the structure is, of course, transmission electron microscopy. In contrast to X-ray diffraction, which can be carried out on a wafer immediately after growth and is non-destructive, transmission electron microscopy unfortunately requires that the sample is made into a very thin section. It's destructive and time-consuming, which means it's difficult to do systematically on every single wafer which is grown. But if it is done, then a very large degree of information is obtained. Here we can see that we can clearly identify the germanium channel, which is almost pure germanium. With electron energy loss spectroscopy, we can identify a composition of around 97%. And here we can also identify the interfaces and how quickly the composition changes from the silicon germanium to the germanium. In order to identify other elements in the material, we can perform secondary ion mass spectrometry. Secondary ion mass spectrometry means that a beam of ions is shot at the sample. This sputters off other elements that make up the sample. These other elements that make up the sample are then subjected to mass spectrometry so that we figure out what they are. Obviously, there is silicon and germanium in the structure, but we need to follow these and then we know where we are in the structure. and you can see the silicon and germanium compositions varying with depth. And you can identify where the quantum well is because you can see the peak in the germanium and the dip in the silicon. Associated with this, you will also see, for example, boron. It's natural that boron, it would be a contaminant in a system that's been used for p-type doping, and also boron tends to accumulate on the surface of wafers which are left in a laboratory. Maybe more critical is also the background of oxygen. And the background of oxygen, which is a major issue which needs to be identified and solved, tends to accumulate more in the silicon germanium than the pure germanium channel itself, but may cause a kind of neutral impurity scattering which is limiting the performance of qubits.